Good morning. We are just waiting about a minute or two for 10 a.m. start. All right. So, just as a quick recap to start off, okay? We are currently working on the topic conservation and dissipation of energy. And previously, we learned about all the different types of energy stores as well as how to calculate for them. So that's what we did previously. So in terms of the energy stores that we did in calculations, we've done elastic potential energy, we've done gravitational potential energy, we've done kinetic energy. And gravitational potential energy was equal to mgh, mass times gravitational field strength times height. Elastic potential energy was a half ke squared, which is, or I should say 0.5 ke squared, which is 0.5 times the spring constant, which is just a measure of how stretchy something is, and E being the extension, so the change in the length of the spring or the elastic band. And kinetic energy was equal to 0.5 mv squared, which is 0.5 times the mass of the object times its speed squared. Looking at this now, you might think these equations look really, really difficult, but we've gone through them. If you need to get a bit more practice, just let me know via email or a comment on Show My Homework for these three equations. You can do it for all of them, you could do it for one of them, but these equations we will come back to at a later date. The main goal of this topic, the general theme, is that there are a lot of calculations. There are a lot of equations for calculating certain types of energy, but they all sort of link together. For you to be successful in these calculations, it is really important that you have a good, strong understanding of what elastic potential energy is, the energy stored in a stretched or compressed spring, an elastic object, gravitational energy stored depending on the height above the ground, kinetic energy stored in a moving object. Okay? So that was just a quick recap of things we have done so far. If you missed out on any previous lessons, there should be all the videos recorded on the YouTube channel under the Conservation and Dissipation of Energy playlist. So, all of these equations, though, are all to do with one object. So calculate the elastic potential energy of this spring. Calculate the gravitational potential energy of this object on top of a building. Calculate the kinetic energy of this moving car. They're all to do with one object because remember, these three are examples of energy stores. So these three. Ooh, hang on. It's lagging a bit. Oh, it's happening again. I'll type it out. change the battery. I'll have to ask my husband about what is the best way to fix this in a sec. So these three are examples of energy stores, which is all to do with how energy can be stored in one specific object itself. But there are other types of energy that are all to do with how energy can move from object to object. We call that movement of energy, energy being transferred. So for example, if we had like a football being kicked across the grass. It's losing kinetic energy as it's moving. Remember the law of conservation of energy. That energy can't just disappear. When the football slows down and it loses kinetic energy, it's not like kinetic energy has just disappeared to nowhere. It needed to have gone somewhere. That's the law of conservation of energy. Energy needed to have gone somewhere. Well, where did it go? It got transferred to that football surroundings. So, when it comes to energy transfers, we're always talking about leaving the object or entering an object from somewhere else. Right, hopefully this works. Okay. It still is not. Sorry, I'm just going to try to change the display capture so it stops, because it was working earlier and then it just stopped. Okay. Okay. Right, I'm going to have to bite the bullet and type it out. Let's do bigger font. So let's think about energy transfers. Sorry about that, guys. How energy can be transferred from one object to another. Well, one thing that you can think about is electrical energy. We talked about this in lesson 1 already, but this is just a quick recap of different ways that energy can be transferred from object to object. So electrical energy is like an energy carrier, where say you had a battery that stores chemical energy. Well, it's going to transfer its chemical energy to, let's say, a motor that has kinetic energy. Well, to get it from that battery to that motor, we needed to have an energy transfer in place, which is electrical energy. You can also transfer energy to an environment. So for example, in terms of light, you have a light bulb transferring its energy in the form of light and spreading it out into its environment. You could also have heat as a form of energy transfer. So for example, a radiator, it's spreading its heat energy out into the environment, transferring it from itself to the environment. But you can also have something that is a little bit unique, that isn't an actual storage of energy, it isn't an actual type of energy itself. So we have electrical energy, light energy, heat energy, but we can also transfer energy that isn't like an actual type of energy itself. It doesn't have to be an energy transfer. It does not have to be a type of energy. It can also be what is known as mechanical work, which is basically energy transferred by a force. As an example, let's say you are pushing a rock to the top of a hill. P with Joe is no longer giving you the challenge you need. You decide for your morning exercise you are going to be pushing a rock to the top of a hill. Well, what type of energy is the rock gaining? As it's moving upwards, think about what type of energy stores there are. There's going to be a change in the rock's energy. It's moving upwards, so the rock is gaining gravitational potential energy because it's gaining in height, right? But like we mentioned earlier with the law of conservation of energy, that additional increase in gravitational potential energy can't have just come from nowhere. It needed to have come from somewhere. It needed to have been transferred from an outside source. That outside source being you. You pushing the rock to the top of the hill. You're giving it your energy, and then that energy is getting transferred to become gravitational potential energy as the rock increases in its height. Well, now think about you then. Well, where did the energy come from that caused you to be able to push this rock up? Well, you had chemical energy in your body, in your muscles, so you have chemical energy in your muscles. You're transferring it to the rock, increasing its gravitational potential energy. But to get from one to the other, to get from you to the rock, we needed to have a form of energy transfer. We needed to have a force. And that is the way the energy transferred from you to the rock. And we call this mechanical work. Basically, when energy is transferred by a force, by a push or a pull. And remember the unit of force you would have learned back in Key Stage 3. The unit of measurement for force is newtons, or N. So there's this formula that unites the force needed for an energy transfer with how much energy gets transferred. And that formula we're going to learn about in a second. And this formula is actually quite important if you want to go into anything like engineering or anything like that. So when we measure how much force we have, that's actually pretty easy, measuring how much force we have. Like we have machinery that can be calibrated to exert a certain amount of force. We can know how much force we are producing pretty easily. And in paper 2 topics, we're going to look at sort of how we can know how much force we are exerting. But right now, I just want you to understand that it is very easy for us to know how much force we are outputting. But we don't really have a way to tell or to quantify and put into our experience in terms of engineering why knowing how much energy there is matters. So let's say, for an example, that we wanted to lift a piece of furniture to the top floor of a block of flats. Well, I can know how much extra energy that piece of furniture needs to be given. Because for it to go up, it needs to gain in gravitational potential energy. And remember, GPE equals mgh. If I know its mass, if I know the mass of my settee or whatever I'm lifting, my gravitational field strength, I know that on Earth is 9.8. And if I know how high I want to lift it up, I can calculate I can easily calculate how much energy it needs to gain. I can easily calculate how much energy my settee needs to gain for me to lift it up to the top floor of a block of flats. But you might be thinking, and you'd be correct in thinking, okay, so what? I've calculated how much energy it needs to gain, but I still don't know how much extra effort I need to put in. I don't know if I need to be renting out a huge piece of machinery like this giant crane to lift it up, or if I can work with something smaller. I don't really know how knowing how much energy this piece of furniture needs applies to me. That is why we want to unite force and energy into one equation, one formula, because if we can somehow translate how much energy we need to how much force we need to input to have that amount of energy gain, that would make life in engineering a lot easier for us then. And this is what the formula is. W equals Fs. I'm also going to write another version of this, W equals Fd. W equals Fd now, I think you guys will probably prefer it more once I tell you what all of each of the letters means. The only reason why S is used is because later on in paper 2, we are going to be using S for distance. Okay. So W is work done. Work done is basically how much energy got transferred by the force. You push a rock up a hill, how much energy did you transfer to the rock? You lift a piece of furniture up to the top floor of a block of flats, how much energy did you transfer to that piece of furniture? Work done is the energy transferred by the force. And because it's an energy transfer, it is measured in joules because it is energy. It's just how much energy got transferred. May the 4th be with you as well. F, as you can imagine, stands for force. It's the force that is used to make the energy transfer happen. So force and because it's a force, it's measured in newtons. And I'm going to put S/D. Oh, it keeps capitalizing it. Shouldn't be capital. Come on, don't capitalize it. There we go. S equals distance. This is why I mentioned that you might prefer to use D instead. However, it's like not just general distance. It is a specific distance. It's distance moved in the direction and that's standard measurement in meters. That's the reason why we use S instead of D, because D for distance is just pretty much like how far did you move. But with S, it's like a special distance. If you follow the year 10 forces and balance stream, S is pretty much displacement. S is how far you moved in that specific direction. So we like to use a different letter that isn't distance. So think of it as distance for now, but if you're in year 10, you're going to go more in depth on the special type of distance because it is distance in a specific direction. Okay, so the formula is W equals Fs. A lot simpler of a formula compared to all the formulas earlier on. K equals 0.5 mv squared, EP equals 0.5 ke squared, mgh. Those formulas, you've gotten through the hard part now. Now we have a simple 3-variable formula, but we still have to do the standard FIFA method where at the very start you make a list of everything that a question's given you, and then you write the formula out, insert in the values, fine tune it, and then give your answer at the very end. So still the same method for any formula that we use in physics. Now here's an example. Let me do it in a different color because I'm sick of having it all in the same color. Oh, I like this color. Example. Calculate the distance an object moved when 300 kilojoules of energy was transferred by a 50 Newton force. Okay, so this is the example. Get out a piece of paper and follow along with this. Even though we just learned work equals force times distance, some of you guys might be able to even go straight ahead now and calculate this based off of your skill in FIFA, in using formula, insert values, fine-tune, answer. Because it is the same principle no matter what formula you use, as long as you can identify all the variables. So the first thing I'm going to do, remember, is just read through from left to right in our question, and anytime they give me a value or tell me what value they want me to calculate, I am going to write that down and make a list. So calculate the distance an object moved. So calculate the distance. They told me to do something. I need a distance. Moved when 300 kilojoules of energy. So 300 kilojoules of energy. That's the number of energy they gave me. But remember, I need energy in joules. That's the standard unit that has to go into all formulas. Energy needs to be in regular joules. Because it's 300 kilojoules, I just times it by 1,000. Kilo means 1,000. Think back to maths. So I have 300,000 regular joules. Just like how there's 2,000 meters in 2 kilometers. Kilo means 1,000. When 300 kilojoules of energy was transferred by a 50 Newton force. So force equals 50 N. And that is standard newtons. Then, first step, I write my formula, W equals Fs. Remember, at this stage, I'm not going to be too fussed if you use D, but it is just, I have to stick to what is convention in physics, meaning what is the proper way of doing it. The proper way of doing it is writing it as S, but I completely understand if you think I have no idea why S is being used for distance. So my formula is being stated. Next step, I insert my values. So I just look at my list and I look at my formula and I look at each letter of the formula and then see on my list if there's something I can substitute in. So W, which is work done, how much energy got transferred. Do I have an energy transferred? Yeah, I have 300,000 joules of energy was transferred is equal to, do I have something for F, my force? Yep, I have 50 newtons, it's up here. 50. And then do I have a distance traveled? No, I do not, so I'm going to leave it as that. So that's 1 mark for me already. I've inserted all my values. Remember, what I recommend is looking at the formula and go each letter from left to right. Each letter, look at your list to identify if something can be substituted in. Don't try to substitute in all at once, because that might be a bit difficult if you're just starting to get a handle on these formulas and equations. So work 1 letter at a time, checking your list systematically, and then get that 1 mark for inserting values. Next, fine-tuning it. Basically, the rearranging part, solving for the variable. Well, our missing variable is s, our distance. So once again in maths, we have to get that on its own by doing the opposite to anything that's on its side. Meaning, if we want s on its own, we want to get rid of this 50 here. And remember, to get rid of something, we have to do the opposite to it. So I need to divide by 50 because this is 50 times. So if I divide by 50, I can get rid of it. Let me rewrite this. Times s. So if I divide both sides by 50, that looks a little better. These 50s here cancel out on the right hand side. And I'm left with 300 divided by 50 equals s. And then I stick in my calculator or I do it in my head. 300 divided by 50 is going to be 6. And that is my final answer. And I put the unit in, 6 meters, because that is a distance. So in terms of, oh, I should write answer. So in terms of our calculations, I am hoping, beyond hope, that you guys see the theme in all of the calculations that we've done in this topic. Our method was exactly the same. And the reason why I want you guys to see that is because I don't want you to get overwhelmed with all of the formulas and equations that we have, right? So far we've done 3, counting today we've done 4. So it's quite a lot of calculations that might make you feel a bit overwhelmed because it might seem like, oh, you have to learn how to calculate for kinetic energy, and then you have to... Oh, shoot, absolutely correct. Yeah, 6,000. Thank you very much, Louis. That was my mistake. I accidentally left out the extra zeros when typing. 6,000. Spot on. Thank you very much. That was the classic intentional mistake, just to check that you were paying attention. Or you can give your answer in kilometers. Alright. So basically what I was saying was that I don't want you to think that because we have 4 different equations, we have 4 different methods. Where you think, oh, I gotta learn how to do kinetic energy equation, and I gotta learn how to do gravitational potential energy equation, and elastic energy, and work done. I don't want you to have that mindset, because it is, no matter what formula it is in physics, it's the exact same method of making a list, Formula, insert values, fine tune, and then giving your answer. And the only different skills in between, the only difference between each formula is just how you would have to end up rearranging it when you get to the fine tune section. But all of the skills involved in that is the exact same as you do in maths, where you just clean it up a bit and then do the opposite to rearrange. So sometimes with some formulas, you might have this fine-tune section might be a little bit longer, but it's still the exact same skills. Okay, so now for a bit of, I'm going to actually put on, before we get into practice, a challenge question. And this challenge question is basically testing your understanding of work done. And I'm going to be a bit mean and connect our kinetic energy equation to this. That should be squared, but right now I can't change it to a little 2. Hang on, I'm going to actually write it. The screen might go black a second. So KE equals 0.5 mv squared. It's very strange. It's like it doesn't like it when I'm writing. Okay. So let's say we have our example of our football being kicked along a patch of grass. Well, the way that the energy was transferred from the football to the ground was through a force, was through friction. The only reason why the football's not traveling forever after you kick a football isn't just going and going and going and never stopping, is because eventually friction, which is a force, slows it down. So friction did work on that football. And the work that it did was the energy that was transferred from the football to the ground via friction. So let's say the football started off I'm gonna say I don't even know how much footballs weighs. To make your calculation easier, I'm gonna say it weighs 1 kilogram. How much does a football weigh? How much mass does a football have? I don't know. You kicked a 1 kilogram football and it had a initial speed of 5 meters per second. A little while later, it slowed down to 1 meters per second. Calculate the work done by, not calculate, state the work done by friction. So that is my question, and that is very common exam style wording, because you might think, work done. I see the words work done, that means I'm going to use W equals Fs. But notice I didn't give you a force in this question. I didn't give you a distance traveled in this question. But I still ask you to tell me what the work done is. So this question basically probes and sees if you understand what work done actually is, in that it is an energy transfer. I'll let you have a think about how you might approach this question. Remember, work done is an energy transfer. If you're completely stuck, that's fine. I'll talk you through it in a second, but I do want to give people some opportunity to have a think about how they might approach this question. Okay, let's talk it through now. Right. So one thing that I want you to notice. Obviously, the mass of the football doesn't change. Mass equals 1 kilogram. Initial speed 5 meters per second. Once again, I'm just making a list of everything I know. Oops. Final speed equals 1 meters per second. Work done equals question mark. But this is energy transfer. Right. If you notice, this football lost speed. It started off at 5 meters per second and then it went down to 1 meters per second. Because it lost speed, it must have lost some kinetic energy. Because if you look at the kinetic energy formula, it's a half mv squared. So if you have a smaller v, which is your speed, you're going to have smaller kinetic energy. The mass of the football stayed the same, so the only thing that changed was v, but still that meant that because the football slowed down, it lost kinetic energy. Now back to something we talked about all the way back in lesson 1 of this series, the law of conservation of energy. It lost kinetic energy, but that kinetic energy had to have gone somewhere. It cannot be just created, like it cannot just disappear in thin air of this football lost energy, now that energy is gone from the universe, never to return. That's not how energy works. Energy is conserved. It is cannot be created or destroyed, only transferred. So that loss of kinetic energy of the football was a gain in energy elsewhere. So let's think about where that energy could have gone. Well, it could have been transferred as heat to the ground as it rubbed against the ground with friction. It also made a little bit of sound, right? Because it's not going to be completely silent as it's rolling around the grass. It lost a bit of energy as sound. But the main cause of this was the force of friction, meaning our force, friction, did some work. And the work that it did was how much kinetic energy was lost. So in this question, if you find how much energy was lost by the football, then you will know how much energy was transferred, so the work done, which is an energy transfer, by friction. So you don't actually need the equation W equals Fs. The only equation that you need is Ke equals 0.5 mv squared, which is basically just your way of calculating its starting energy, kinetic energy, and then its final kinetic energy. And the difference between those two is going to be how much energy got transferred out by friction. The reason why I'm doing this problem is because this problem basically it surrounds your understanding of work done, of what work done is. Whenever you have a force that acts on an object, you're going to have an energy transferred. Whether it's going to be a loss of kinetic energy, or you push the football a bit more and you give it kinetic energy. Work done is just an energy transferred. It's just an energy transferred specifically by a force. So you could calculate it with work done equals force times distance, but you could also calculate it by knowing how much energy was gained or lost by an object due to a force. So let's calculate this. So I'm going to do starting kinetic energy was 0.5 times 1 times 5 squared. Because I can't actually do my little squared symbol on here right now, I'm just going to do 5 squared is equal to 25. And that, oh, they calculated it for me straight away. That is 12.5. And that is in joules. The final kinetic energy was, once again, 0.5 times a mass of 1 times final speed is 1 squared. 1 squared is just 1. And that is 0.5 joules. So its starting kinetic energy was 12.5 joules. Its final kinetic energy was 0.5 joules. I calculated this just from using the same formula for kinetic energy as we have been using, 0.5 mv squared. The only difference is I didn't, like in this last bit here, instead of actually going 5 squared, I just directly made it 25. Reason being is because I can't really do superscripts easily on here. So I just made it 25 instead of writing it out fully to start with. So the difference in kinetic energy was 12 joules. That means that our football lost 12 joules of energy. That then means that our friction did 12 joules of work. Because it transferred 12 joules of energy out from the football and into the environment around the football, so the ground. Okay, so I just wanted to do that example to highlight what work done is. That was the point of the example. Beyond the calculation, it is really important that you understand that work done is just what we call an energy transferred when a force is doing the transferring. That is all that work done is. And so whenever you have something that gains or loses energy because of a force, that is work done. Even if you're not using the W equals Fs equation, you're still finding a work done because you're still finding how much energy was lost or gained. So that's the key takeaway here. Alright, now back to the work done equation itself though, because it is important for you to learn how to use the formula. I'm going to have one on here for you guys to do, and then we're going to go over the answers after you do it on your own. and then link you to some practice while I get the answers up for it. Calculate the force required for 9 joules of work to be done over 90 centimeters. So that's my question. Get out some scratch paper, your calculator, and have a go at this one. Meanwhile, I'm going to put a challenge at the bottom. There we go, my super challenge is up as well. Let me just scroll down so you don't see. There we go. So the super challenge is less of a super challenge because of the maths and more of a super challenge because you really have to think your way around it. And just like the one we did previous, it is you understanding what work done is, how it links to force, and how it links to energy. For those of you doing the super challenge, I will just quietly now put up the answer to the first one. So for the first one, you should have gotten force is equal to 10 newtons. The tricky bit from that one was remembering to make sure you convert the centimeters to regular meters. That would have been a mark on its own as well. So this bit is a mark. If you forgot to do that, you would have still gotten follow through. You would just have lost a mark for forgetting to convert. You would get a mark for substituting things incorrectly, and then a mark for the final answer. So we should have gotten 10 newtons for the first one. Calculate the force required for 9 joules of work to be done over 90 centimeters. Hopefully we were all right on that. Okay, let's break down the super challenge then. Unless anyone wants more time on it, please write in the chat if you want me to stop to give you a little bit more time to work it out. Okay, we'll have a go at the super challenge then. Right. So, a crane moved the sofa to a flat 100 meters high up a tower block. The mass of the sofa is 5 kilograms and the gravitational field strength on Earth is 9.8 newtons per kilogram. What was the force needed by the crane? So, the reason why it's a super challenge again is because it's less to do with the maths and more to do with you had to connect the ideas of energy, force, and work done. So the first thing you have to realize is that the energy change due to a force is basically known as work done on that object. So our sofa changed in its energy because it got lifted up. When it got lifted up, it changed its height, therefore it changed its gravitational potential energy. It gained in some gravitational potential energy. That energy, once again, didn't come from nowhere. It came from our crane. And to transfer that energy from the crane to the sofa, we have mechanical work. We had a force doing that energy transfer for us. So if I work out how much gravitational potential energy it changed by, so if I worked out its change in gravitational potential energy, then I know how much work done was done by the crane. So, we're assuming that it started from ground floor, meaning like from 0 meters up high. So its gain in gravitational potential energy, we use mgh is our formula. You do have to memorize that formula. The only formula you don't have to memorize in this set is the elastic energy formula. But GP equals mgh, you do have to know that one. So GP E equals, I'm substituting in values. Mass, I do have a mass for my sofa. It's 5. Gravitational field strength, 9.8. Height is, it went up 100 meters. I stick that into my calculator because I will not be able to do that myself. 4,900 joules of energy. And that 4,900 number is my gain in gravitational potential energy. Therefore, that is the work done by the crane because that was our energy transferred to the sofa. So work done is not something that is just unique on its own, like a different type of energy. Whereas you have different energy stores that are separate from each other that can be transferred between, but like separate sort of ideas. Work done is just energy. So the energy transferred could be gravitational. The work done could be kinetic. The work done could be elastic. Work done is just an energy transferred by the force. So the gravitational potential energy gain is the same as the work done by the crane. It's the same thing. So therefore, work done was 4,900 joules as well, because that was how much energy got transferred to our sofa. Now the question asks, what was the force needed by the crane? So I am thinking we gotta use our formula, work equals force times distance, because that is the formula that translates energy and force. That's the formula that links those two together. Our work done, as we just worked out, was 4,900. Our force, that's what we're trying to find, we don't know yet. We're just substituting in our values. And then our distance traveled was how high it went up. Which is 100 meters up our tower block. Now, once again, we're solving for F, so we have to get rid of the 100 by doing the opposite. We're dividing both sides by 100. And then we are left with 49 newtons of force needed. You don't actually have to write that full sentence. I just wrote it there just for you guys to understand what we'd done. So we worked out how much force we needed to do a certain amount of work. And that work that we wanted to do is basically how much energy we wanted to change about an object, how much energy we wanted to transfer to an object. And in this case, our work done is transferring it into the form of gravitational potential energy. So all of these concepts are linked together. They're not separated from each other, they are linked together. Okay, so a bit of practice then. I'll link our practice on here. If you go to that link and click on lesson 5 work done, you'll see on there an equation bullseye. Obviously you don't have to if you feel a bit confident with this, that's fine. You don't have to do it all. Remember, this is all completely optional, just to help you out with feeling a bit more confident. So don't feel obligated to do the whole sheet. But I will put answers up to all of these questions. Expect it within the hour. I will have to check through. And if when you see the answers posted up and there are any ones that you feel like you're not really sure how I got that answer, please let me know. Leave a comment on Show My Homework, or send me an email, or leave me a comment on this YouTube video. And then I will see if I can help out with that. But the main key bits is understanding what work done is. It's nothing special, it is just an energy transferred by the force. How much energy got transferred by force. And that energy transfer could be in different forms of energy. Could have been GPE, could have been kinetic, could have been elastic, whatever it was. If it was done by force, we call it work. Okay? So have a go at those problems if you would like, and then I say the hour, that is the absolute latest. I'm gonna get started on it now, so more realistically it will be like 15 minutes time that the answers will be up on there. Okay? Right guys, have a good rest of the day. That was a longer session, so well done everybody.